Hi, so this is my DO2 presentation video, and my name is Kevin Santos, and I'll be talking about some Ramsey theorems in Euclidean geometry. So as a motivating example, I started off with the theorem of friends and strangers, which says that if we have a group of 6 people, we can prove that among them there must be 3 mutual acquaintances or 3 mutual strangers. Now we can represent this problem using a graph. If we think of the vertices as people and the edges as their relationships, so we can color an edge red if the 2 people are friends or acquainted with each other, and we can color the edge blue if 2 people are strangers. Now, by the pigeonhole principle, if we look at the 5 edges emanating from one vertex, since there are 5 edges and 2 colors to choose from, by the pigeonhole principle, at least 3 of those edges must be the same color. So we're guaranteed to have at least 3 edges, say at least these 3 edges be the same color, say blue, without loss of generality. And now let's consider these 3 edges right here. So if any of these 3 edges is blue, then we will have 3 strangers, because we have a blue triangle. If this edge is blue, then we'll have a blue triangle. Or if this edge is blue, we'll have a blue triangle. So in any of those cases, we'd have a blue triangle or 3 strangers. In the other case, otherwise, if all of these edges turn out to be red, then we will have these 3 people be mutual friends. We'll have a red triangle right here. So no matter how we color these 3 edges right here, we're always guaranteed to have at least 1 red or blue triangle. And that completes the proof. That means that there must be either 3 mutual acquaintances or 3 mutual strangers. Now I did want to, oh yes, and as well, we can prove that if we have 5 people, then we aren't necessarily guaranteed to have 3 mutual friends or strangers. So if we have the complete graph on 5 vertices and we color each of the edges in this way, then in this coloring, there are not any red or blue triangles. There's no triangles with all red sides or all blue sides. So if we have 5 people, the above result isn't necessarily guaranteed. And I do go over the significance of this a bit further in the paper, and I also do explain Ramsey's theorem. But I found out that I don't really have that much time to go over those theorems, so I will just go over the proofs of some of the later theorems in the paper. And to do that, I'll do some definitions right here. Now, first of all, an R coloring of the Euclidean plane is a map where we assign each of the points in R2 to one of R colors. So if we just imagine the Euclidean plane as just a bunch of points, then we're sort of just coloring each of those points some combination of colors. And a set S is monochromatic if each point in S is assigned the same color. So like these 3 red points would be monochromatic. And now let's define what it means to be R Ramsey. If we have a finite set of points in the Euclidean plane, the set of points is R Ramsey if for any R coloring of the plane, there is a monochromatic set of points congruent to that set. So we can actually prove that no matter how we color the points on the plane with 2 colors, we can always find 2 points in the same color distance 1 apart. So if we let P be the pair of points unit distance apart, then P is 2 Ramsey. So no matter how we color the points on the plane, if we color them either red or blue, then we can always find 2 points unit distance apart that are the same color. And that's pretty clear if we look at an equilateral triangle with unit side length, because there's 3 vertices here. And if we are coloring them with 2 colors, that means that by the pigeonhole principle that 2 points must be the same color. So we will always have 2 points of the same color unit distance apart. And in addition, P is 3 Ramsey. So no matter how we color the plane, if we use 3 different colors, then we can always find 2 points of the same color unit distance apart. Now to show that, we'll consider this graph right here, which has all edges unit distance length. And let's consider this vertex right here. So let's assume that there are no points of the same color unit distance apart. And we'll lead that into a contradiction. So if we assume that this point is red, for example, then if we assume that there are no points of the same color unit distance apart, then this point must be a different color, and this point must also be a different color, say blue and yellow. So that means this point A must be a different color from those 2 points. And similarly, in this triangle right here, these 2 points must be different colors from A. So let's say they're also yellow and blue. But in the end, no matter how we choose to color those points, this is yellow and this is blue, for example, then this vertex must be red in order to avoid having 2 points of the same color unit distance apart. But if that's the case, then we'll still end up with 2 red points unit distance apart. So that's where the contradiction lies. If we assume that there are no points of the same color unit distance apart, then we won't really have a way to color this one without breaking that assumption. So that assumption must be wrong, and no matter how we color the plane using 3 colors, we'll always be able to find 2 points of the same color unit distance apart. Okay. Now let's ask the next question, which would be about triangles. Can we always find a monochromatic triangle who's congruent to a given triangle for any 2 coloring of the plane? Well, it turns out that that's true for the 30-60 right triangle with side lengths 1, root 3, and 2. And with this triangle, no matter how we color the plane using 2 colors, we can always find a monochromatic triangle congruent to that triangle T. And that follows directly from these 2 lemmas. So if we let T be a triangle in R2 with side lengths X, Y, and Z, and we consider any given 2 coloring of R2, as long as there is a monochromatic equilateral triangle with any of these side lengths X, Y, or Z, as long as there's at least one of those equilateral triangles whose points are the same color and whose side length is any one of X, Y, or Z, then we can guarantee that there exists a monochromatic triangle congruent to T. And it turns out that it's true. We can always find at least one monochromatic triangle whose side length is either 1, root 3, or 2 for any given 2 coloring. So from these 2 lemmas, it follows pretty directly that this triangle with side lengths 1, root 3, and 2 is 2 Ramsey. So let's prove these 2 lemmas. Let's let T be a triangle in R2 with side lengths X, Y, and Z, and we'll consider a given 2 coloring of R2. So as long as there exists a monochromatic equilateral triangle with a side length of either X, Y, or Z, so let's just assume without loss of generality that we have a monochromatic equilateral triangle with side length x, and all the points in it are red. The same argument would apply if we have one of side lengths y or z, but we'll just start with x for now. And we can adjust this angle in this diagram here. These are two equilateral triangles, by the way, and so is this one. We can adjust this angle here in this diagram so that this triangle is congruent to the triangle T, the original triangle that we want. And let's do another proof by contradiction. Let's assume that there are no monochromatic equilateral triangles, let's assume that there are no monochromatic triangles congruent to this triangle T, and we'll lead that into a contradiction. So just to make it clearer in this diagram, if we assume that there are no monochromatic triangles congruent to the original triangle, then this triangle can't be monochromatic. So this point must be blue since these 2 points are red. And similarly, this triangle is actually congruent to the original. So this one must be blue since it can't be monochromatic under the assumption. And similarly, this triangle is congruent to the original T. So this point must be blue. And as well, it turns out that this triangle here is congruent to the original triangle T. So if we assume that it can be monochromatic, then this point must be red. Now let's consider this point. What color can this point be under the assumption? Well, you can see how it clashes with these two triangles here. These two triangles are congruent to the original triangle. So they both can't be monochromatic, but if this point is blue, then this one will be monochromatic. And if it's red, then this triangle will be monochromatic. And we assume that we can't have any monochromatic triangles congruent to that original one. So we led to a contradiction here where this point can't be colored. That means that we must have at least one monochromatic triangle somewhere in this diagram that is congruent to the original one. Okay, and the next lemma, we want to prove that for any given two coloring of the plane, we can always find at least one monochromatic triangle, equilateral triangle, whose side length is either 1 or √3 or 2. So as we proved earlier, for any given two coloring of the plane, we can always find 2 points of the same color, 1 unit distance apart. And then let's assume, proving by contradiction again, that there are no equilateral triangles I can't really write, but there are no equilateral triangles with side lengths 1, √3, or 2, and then we'll lead that to a contradiction. So if we assume that there are no unit equilateral triangles, then this point must be blue, and so must this point. Then here, this triangle highlighted here has side length √3, so it can't be monochromatic under the assumption, so this point must be red. And here we have an equilateral triangle of side length 2, and we assumed that that can't be monochromatic either, so this point must be blue. And then now, let's look at this point. So if this point is blue, then this will be a monochromatic unit equilateral triangle. And if this point is red, then we'll have a monochromatic unit equilateral triangle here. So that goes against the assumption that we don't have any equilateral triangles of side length 1, √3, or 2. So we led to a contradiction where this point can't be red or blue. So the assumption must have been false, which means that we should always be able to find a equilateral triangle whose monochromatic and whose side length is 1, √3, or 2 for any given two coloring of the plane. And there we go. So I don't have much time to cover much else, but My paper will also go into some of the extensions of Ramsey theory. And yeah, thank you for listening.